However, this is only a pseudo solution because there is still one question left. What's the question? Okay, so the question is, for customers with the same value of COSI ID, can they use the same key to encrypt sensitive attributes? The answer is, unfortunately, no. Because in this way, one customer can decrypt another customer's sensitive attributes when they are using the same key. So then what can we do? We want to make each customer has a different key, different encryption key for her sensitive attributes. But on the other hand, we still want to ensure each of these keys is derivable if and only if there are at least k customers having the same COSI ID. So how can we do this? Well, we do this using 2NK Shamir secret sharing. So in this 2NK Shamir secret sharing, we set up for each value of COSI ID, we set up a degree k-1 polynomial, and each customer knows 2 points on this polynomial, and the key for encryption is decided by 1 point on the polynomial. The other point is submitted. So let me show you this figure. So you can see here we have 5 customers with the same COSI ID. Okay? So we build a degree k-1 polynomial for them. And we have two kinds of points on this polynomial. The red points are submitted to the miner, and the green points decide the encryption keys of different customers. And we can see, different customers have different encryption keys. Okay?
Can you explain why are you doing this again? Why are you having 2 points for each?
2 points for each?
For each customer. Why are there 2 points for each customer?
Because we want to separate, we want to have each different customer has a different encryption key, okay? So if they have the same key.
So by key you mean the share? Their share?
No, the key. The encryption key of.
But the encryption key is the intercept of this figure, right?
No. This figure is built. This is a new solution. This is not equal to the previous pseudo solution.
I guess the question is, what's the relationship between the encryption key and the point on this curve?
Encryption key and so the encryption key. So this for each customer we see each customer has a green point here on this polynomial, and her encryption key is a function of this green point. Is that clear?
And everyone has a different function, or?
Same function.
Do you have an example?
And a public function. Public function and the same function. Okay, clear?
So is this function have certain properties, or it's just any function?
This function, well, not any function works because we have some other subtle points here, which I don't want to explain, which would bring things to even complicated scenario. But I mean, here you don't. So here for the rough idea, you don't need to consider any additional property of this function.
Because the function has to avoid hitting the red point. And the function should not evaluate to red, right?
Oh yeah, yeah. Oh yeah. So yeah, you are right. So actually, one additional property of this function is that it has to be one way. you want, so if you know this green point, you can figure out the encryption key, but not the reverse way.
Are the x coordinates of this point public information?
Yes. Okay. So the idea is here is that the green points are submitted to the miner. Okay. So let's consider the case where k customers having the same quasi IDs. Then the miner receives k red points on this curve. Thus, he can interpolate this curve using these k red points, and because the x-axis of these green points are public, he can easily figure out all these green points, and then he can derive the encryption keys.
But here you violate one thing. You assume you need k customers, right? K customers to derive the key.
Yes.
But here you need k over 2 customers. If each customer decided to send both his red and green points, then you will only need k over 2 customers.
Well, we only consider semi-honest case, which means all these customers follow the protocol, but they are curious.
So if they follow the protocol, you don't need 2 points.
Follow the protocol, don't need 2 points. Why? Why not?
Because if you assure that each one of them will use 1 point, then and not disclose that point to anyone, this means that they are that no one can derive their point, so you don't need the other point.
But how can the miner derive this point?
Of course, they would send it to the miner, but I don't until now see why you need 2 points.
Do you have an example that shows this in action? Do you have any example?
Sorry, I don't. So, so the point is that you want to allow the miner to derive these encryption keys if and only if there are k customers, at least k customers, having the same quasi IDs. So if each of them simply submits an independent encryption key, then no matter there are k such customers or not, the miner is always able to derive the encryption key. Is that clear? Okay. Sorry, this is pretty theoretical stuff, and just cannot give more concrete illustrations. So this explains the solution to our first problem formulation. So I need to go quickly because the second formulation is much more complicated. So in the second formulation, the centralized algorithm we consider is the MW algorithm, which uses suppression to k-anonymize the table. Okay, you can see various entries are replaced by stars. This is called suppression. Okay, and the privacy guarantee we want is that the miner should not learn the suppressed entries. So if the miner does not know these suppressed entries clearly, all he sees is just this k-anonymized table and nothing else. Okay? Is this clear? This MW algorithm is pretty complicated. It includes 3 phases. In the first phase, it computes the distance between each pair of rows. So what's the distance?